Raoult's law, now we have to get our S's right. Solvent, solute. Raoult's law relates to the solvent. It says, what's X stand for? Mole fraction. The mole fraction of the solvent, how much pressure, the equal vapor pressure of the solvent will be equal to the mole fraction of the solvent. And then what's P naught? Yep, the original one, with the pure substance. When it's pure state, what's its equilibrium vapor pressure at that temperature? So mole fraction times what it is in its pure state. Very good. Yes. We talked about ideal solutions, and I don't know if you remember, but ideal solutions are where you're taking two things and you want to mix them together. So what you have to do is break those bonds, and then they're going to form new bonds. So there's energy required to break the bonds, and energy is released when the new bonds are formed. So ideal solutions is that those energies are equal. Okay, so Raoult's law applies really well to ideal solutions, and that's what we mean by an ideal solution. Raoult's law will apply to anything that's volatile, any volatile component in the solution, and even for non-ideal solutions, Raoult's law works reasonably well. So if we consider two things mixed together, A and B mixed together, of course you would say if you only have two things, then if you add up their mole fractions, they better be equal to 1. That makes sense. Well, we could go and we could say, actually this is Dalton's law of partial pressures. According to Dalton, the partial pressure, is that right? No, this isn't a Dalton thing. This is actually Raoult's law, sorry. According to Raoult's law, the pressure, the equilibrium pressure of A will be equal to the mole fraction of A times A if it was pure. Hi.
I'm sorry.
You're fine. The equilibrium pressure of B will be equal to the mole fraction of B times the partial pressure, or times the pressure of B if as opposed to pure state. This is kind of interesting. It's almost like they run interference for each other to go ahead and go into the liquid to evaporate into their gaseous state. I think that's kind of neat. So the total pressure then in the headspace above your liquid, the total pressure would be equal to, you just add these pressures. Okay, so again, what are we talking about? I got new markers. Yay! Okay, here's my beaker. Here's my watch glass, like really seals the system, right? Down here we have A and B. Okay, you're going to end up, these are liquids, you're going to end up with A gas and B gas, okay, and they kind of run interference to evaporate, but they will go ahead and reach equilibrium, okay, and then what we know, according to Raoult's law, is that in this headspace above your liquid, the partial pressure of A will be equal to the mole fraction of A times the pressure of A as it was in its pure state. Okay. The partial pressure of B will be equal to the mole fraction of B times the equilibrium pressure of B as it was in its pure state. So that's kind of what we're talking about there. Actually, though, this scenario assumes that they are both volatile. Do you kind of see that? They're both volatile. Why do I say that? Because I see them in their gaseous state. Well, what if one of them is not volatile? Well, in that case, it still runs interference, so to speak, as the way I think of it, according to Raoult's law. Okay? But if it's not volatile, you're not going to see it in the headspace up here. Okay? So in that case, we have A and B in here, and B is non-volatile. Okay, you're going to have evaporation to establish an equilibrium of A, but not B. Does that make sense?
Is that going to make it more complicated to get set pressures and mole fractions?
No, it makes it actually easier.
Okay.
Because the way you calculate the partial pressure of A for both of these is the same. The mole fraction of A times the equilibrium pressure of A if it was in its pure state. So it's the same thing. It makes it a little easier because you don't have that B going up. You just have A going up because B is non-volatile. We're going to do some problems like this. So that means that, well, if this is 0, okay, that makes this 0. So let's look at a problem where you're dealing with a non-volatile solute added to a solvent that's relatively volatile. We're going to calculate, we're going to pick on water, and so let's see. I'm about making pictures. Did I take a picture yet? All right. So here's my water. Here's my watch glass to seal it up. It says that I'm going to dissolve 5.00 grams of glucose. Now, I don't know about you, but when I think of glucose, I think of sugar, glucose, fructose, and it's not volatile in general. So it's a non-volatile solute. That mass is added to 100 grams with 4 sig figs of water. I guess we're going to need to know those amounts so we can get a mole fraction of the water, right? That's exactly what we're going to do. The temperature is 90 degrees Celsius. So all we got to do is the equilibrium vapor pressure of H2O will be equal to the mole fraction of H2O times the equilibrium vapor pressure of H2O at 90 degrees Celsius. Let's not make it more complicated than it is. Bless you. Bless you. So I have a couple of tables here, but in these 2 tables you're going to find this, that if in its pure state the equilibrium vapor pressure of water at 90 degrees Celsius is 525.8 millimeters of mercury. So here's the 2 tables, see if we can find 90. I see it. 90 here. And then this table is a little different. I think we've looked at these. These are specific for water. This is just got different like units it goes. Let's see if we can find 90. Okay. Every once in a while you find different constants. I think you probably, if you're looking at my answer, sometimes you're like, where did she find that constant? Well, you probably just slightly different constant than you found. All right, so this is Raoult's law. Our solvent is water. Our non-volatile volatile solute is glucose. So all we got to do is somehow come up with a mole fraction of water. And again, this is why you dragged yourself, or I made you drag yourself through working those solution concentration problems. This one's pretty straightforward, I think. To get the moles of glucose, we have the mass of glucose. We need to use the molar mass to get to moles. Okay, we have the mass of water. We can get to moles there too. So, knocking it out down here, and I'm bad. I mean, okay, what's the molar mass for water? 18.02 grams per mole. Now, I don't know what the molar mass for glucose is, but I'm not going to show you how to calculate it. You know how to do that. So, yes. The mass of water was 100 grams. You guys told me the molar mass is 1 mole per 18.02 grams. So that gives us 4 sig figs. 5.549 moles of H2O. Of course, we'll go in the numerator here in a minute and in the first term in the denominator. And for glucose, we're going to take that 5.0 grams, and the molar mass, this does sound familiar, the molar mass of glucose is 180.16 grams per mole. So 5.00 grams times 1 mole over 180.16 grams. Grams cancel, we're left with units of moles. And only 3 sig figs, so I get 0.0278. moles of their solute, the non-volatile solute. So we're ready to take those quantities and plug them in up here. So the mole fraction of water is equal to 5.549 moles of H2O divided by quantity 5.549 plus 0.0278 and the quantity moles of solution. I think we would be allowed 4 sig figs. Remember, this mole fraction should always be less than 1. So I get 0.9950. So it's something. But does this make sense? The closer the mole fraction comes to 1, then the more likely your equilibrium vapor pressure is to bump up against the equilibrium vapor pressure of its pure state. So, I mean, it all kind of makes sense. So now we plug this into Raoult's law, and it looks like this, where the equilibrium vapor pressure of H2O, if you want to, or this is solvent, but you just say H2O if you wanted to, is equal to the mole fraction, which is 0.9950 times the equilibrium vapor pressure for water in its pure state at that temperature, which was 525.8 millimeters of mercury. You know, one of the things emphasizing this class is all about units, but does this make sense? You can use any units of pressure, I mean, and it should come out just fine. So 4 sig figs, I get reduced equilibrium vapor pressure of 523.2, and units would be pressure in millimeters of mercury. So we talked about, you know, when you're working problems, in all science problems, it should make sense. So we talked about equilibrium vapor pressure lowering, which is exactly what this did. And I can't remember if the next slide I come up with that delta P, but we can do that too. Yep, delta P. What was the change in the equilibrium vapor pressure? Equilibrium vapor pressure lowering. So it's always final minus initial. Our final here is the one with that the solute has been added to. So that looks like this. Delta P is equal to quantity 523.2 minus 525.8 and quantity, and then that's millimeters of mercury. So you end up with the sign is negative 2.6 millimeters of mercury. That's your vapor pressure lowering because you're in glucose. So if we add more and more glucose, then that means the mole fraction of your water is going to go down, and that means that your equilibrium vapor pressure will be even lower. It all makes sense. Not everything in science makes sense. To me. All right. So I have one more problem to show you. And this problem actually goes back to this scenario, okay? Where we have 2 or more volatile components. The partial pressure, again, will be can be calculated from Raoult's law. And then the total pressure, and this does go back to Dalton's law of partial pressures, I think. Remember we said that if you have 2 gases like that, our total pressure is going to be equal to the partial pressure of each. All right. I feel like it's like deja vu. We just did this slide. If you have 2 components, whether they're both volatile, like we're going to talk about, or a volatile and non-volatile one, the mole fraction has to be equal to 1. The partial pressures of each will follow Raoult's law. And the total equilibrium vapor pressure will be equal to adding them together. All right, so I think I'm going to erase this, if that's okay with you, and kind of draw a picture. So I have two relatively volatile things. I have benzene and toluene. Feel free to, I could do BEN for benzene, but if you're going to do that, write it somewhere. And TOL for toluene. Okay. Now, I'm going to need these later on. These are the constants. These are because the knots are what they are in their pure state. So in its pure state, the equilibrium vapor pressure of benzene, BEN, is 75 millimeters mercury. I don't have a question yet, do I? For toluene, in its pure state, the equilibrium vapor pressure is 22 millimeters mercury. Which one's more volatile? They're at the same temperature. Why toluene? I think it's benzene. Why is it benzene? Because this is when it goes, this is going from a liquid to a gas. So this is as it escapes. This says that if I go ahead and let toluene escape, or do its whole liquid gas equilibrium, that it's going to be, the pressure is going to be 22. And this one says if I go ahead and let it benzene do its thing, its equilibrium vapor pressure is going to be higher. Yep.
Oh, so it takes more for it to equal out.
Kind of like, I was thinking that the pressure's on the side of that curve thing we were looking at. The temperature's down here, the pressure's here. So, right? So then that means that the pressure at 22, it's turned into a gas, but it won't turn into a gas till it gets up to 75 for the other one. You know what I mean? Now, it has to be a higher.
Yeah.
Am I making sense?
Yeah. I think we're not talking about boiling. We're just talking about.
Oh, there's boiling points?
Yeah,
Okay.
I think. We're just talking about if it's all hanging out at T is equal to 20 degrees Celsius, in the headspace above pure toluene, it's going to be 22 millimeters mercury. In the headspace above benzene, it's going to be shooting 75.
So in that one, it's 22, it's pretty much done.
Right.
Then benzene keeps it a little bit.
Yeah. But yeah, and to me, what I tried to describe is I had two beakers. I had them separated. I had one for toluene and one for benzene. And you just let them go at 20 degrees Celsius. And once they're done equilibrating, yep, your toluene is going to be 22 and your benzene is going to be 75. Yep. So the benzene is more volatile. Yep. Cool. All right. Well, I don't have a question yet there. Here's my question. So down here in my liquid, I'm going to go ahead and have 1 mole of benzene. And I'm going to have 2 moles, 2.0 moles of toluene. Now, before I go any further, what's the total number of moles I have? 3.0. I'm going to say that is N sub T, total moles. Cool. What is the mole fraction of benzene? I think. So it's how many moles divided by total moles? Yep. Yep, that was after. It's 0.33. What is the mole fraction of toluene? Yep. So it's 2.0 divided by 3.0. 2.0 moles of toluene divided by 3.0, 12 moles. And so 0.66 repeating, so 0.67, right? And 2 sig figs. Cool. Well, actually, as we work this problem, I don't mean to make it too complicated. All I got to do is to take the mole fraction times what it is in its pure state. Okay, mole fraction times what it is in its pure state. That's it. So we're going to knock out a few questions though. That's actually going to be the first question. What is the vapor pressure above the mixture for each substance? Raoult's law. How are we going to get the total vapor pressure? Add them together. Yep. Exactly. The next one's a little more interesting, And to do this last one, we're going to use Dalton's laws of partial pressure. Let's see if I butch this. I haven't butched anything too bad this morning. Well, just a little bit. The partial pressure of A is equal to the mole fraction of A, times the total pressure. That's it. That's Dalton's law of partial pressures. So we're going to knock out mole fraction of A. So if I rearrange that, what do I got? That's proper English. The mole fraction of A, now this would be in its gaseous state, not in the liquid, is going to be equal to what? The partial pressure of A divided by the total pressure. That's Dalton's law of partial pressure. So here we go. This actually is the reason I did this on the board, because you came up with the mole fraction of benzene, 0.33, the mole fraction of toluene, 0.67. I don't know why in my slides I don't show that calculation, but hopefully you're okay with that. Where did the 0.33 come from? 1 divided by 3. Where did 0.67 come from? 2 divided by 3. All right, so then this is applying Raoult's law, okay? So like I said, and this is where to me, I like to write a picture because I get my benzenes and toluenes mixed up, right? So I'm going to take the mole fraction of benzene, which is 0.33, times the vapor pressure of benzene in its pure state, which is at 75 millimeters of mercury. I get 25 millimeters of mercury. Is the partial pressure of benzene. Toluene, I'm going to take its mole fraction, 0.67, and multiply it by what it was in its pure state, which is 22 millimeters of mercury. Down to 2 sig figs, I get 15 millimeters of mercury. That's question 1. Question 2, you told me just add them, and you're right. So the total pressure, the total vapor pressure here is 25 plus 15 units are millimeters of mercury. So notice that I'm careful because it might make a difference down the road to show that I actually know to the nearest ones place. Since I'm adding or around to the nearest ones place, that's why I have to put a decimal here. So it's 40 decimal millimeters of mercury. All right. Then the last little bit looks like this. According to Dalton's law of partial pressure, the partial pressure, this is in the headspace, because we're after the mole fraction in the headspace. So the mole fraction in the benzene in its vapor state, so BN, VAP, and then back, would be equal to the partial pressure of benzene divided by the total pressure. Partial pressure of benzene was 25 millimeters of mercury. Total pressure was 40 millimeters of mercury. I wish sometimes these numbers were different. But, so all we're saying is the mole fraction in its vapor state of benzene, I'll put benzene back, is 0.63. Now, we could actually just take 1 and subtract 0.63 to get the mole fraction of toluene, but we're not going to do that. Well, we could. So the mole fraction of toluene, TOL-VAP, we again take the partial pressure of toluene, which was 15 millimeters of mercury, and we divide it by the total pressure, which is 40 millimeters of mercury, giving it 2 sig figs, and you end up with 0.37. It's interesting. That's my way. Okay, so these will be due on, when we meet again, Monday. I thought I linked to, but I guess not. So off to Henry's Law. Henry's Law is not very long. What's that? Yep, 12. So before we do this, I'm going to see if I can remember, see if you can remember, what did we say with regard to trying to dissolve a gas in a liquid with regard to temperature? Does solubility increase or decrease with increasing temperature? How many people think solubility decreases with increasing temperature? Yeah. I do think, because it's exothermic. So solubility increases with lowering temperature. This actually is just talking, Henry's Law is only talking about trying to dissolve a solute that's a gas. It happens all the time. The effect of, okay, so gas solubility. Now, my video isn't working. I tried to find this video. I can find it, I can show it to you. But have you ever heard this when you open a can and it fizzes? Okay, good. That's all we do, and then it says something. What happened at the factory is, of course, the fizzing is CO2, and the fact that you can hear it means it's actually leaving your sugar water, which is your pop, okay? So what they did at the factory was they before they sealed it, they inserted the CO2 gas, and then they like put an extra layer of carbon dioxide gas on top of that. So it's pressurized, not with air, it's pressurized with CO2 gas. Now here's the deal. The amount of CO2 that can be dissolved in sugar water is a function of the CO2 pressure that's kind of hovering over the liquid. That's Henry's Law, and it makes sense to me. So what happens when we open the pump, when we open our tab, is we go ahead and that CO2 that was there from the factory, it's gone. No, it's a gas. And now, basically, that's why you have your bubbles starting to come out, your CO2 coming out, because it no longer has that headspace pressure. Okay, that's how it works. That's Henry's Law.
So without that extra CO2, it would be flat top.
Yes, yes. If at the factory they went ahead and infused your pop with CO2, whatever way they do it, and if they didn't have that CO2 pressure headspace, they couldn't buy it.
Is there a time limit on how long the CO2 will stay then at the top? Because I've had a pop that was like 2 years old before, and it was not good.
There must be, that might be a permeability issue, or some sort of like, the CO2 must be escaping somehow. So here's a figure from your textbook that does kind of what I was trying to describe. This would be opening the pop, and here you have these cute little CO2, the black The atoms are carbon, the red atoms are oxygen escaping. And why? Because they don't have that CO2 headspace on them anymore. Okay? So if, or you think about, like at home, if we had a little bit of a little CO2 squirt to kind of top off our beverages.
So when you shake a pop, it like breaks that little CO2 layer on top and it all mixes in? Is that why it like explodes?
When you shake a pop, you are, I think I've heard this, it's kind of like, have you ever taken a raisin and put it in your bubbly or something? A raisin, even in carbonated beverage, I think, will allow for your CO2 particles, it gives a surface for them to come together. When you shake it, you're actually allowing them to find each other. And so then they form big bubbles. Yeah. So this is kind of clever. I mentioned headspace. So think of kind of basically this could be water down here, and then we have gas particles here. And the pressure of the gas is, and we've looked at this before, where that plunger can move up and down. So actually the pressure of the gas is a function of that little weight we have on top because it's movable. So now we have two weights, so that thing is squishing down, and again, how it's hovering is a function of the pressure that we have within there. So we have increased pressure here, my point. And I don't know if you can tell the colors. What would you say about the colors of these two?
The second's a little dark.
The second's a little darker, exactly. It's trying to show you that with increased pressure, the solubility of those gas particles is increased. Okay. Increased pressure. Okay, you can even see the gas particles here, and hopefully, it's hard for me to tell up here, but does this look a little deeper blue? Okay. And so that deeper blue is showing you this increase in solubility of the gas particles. Kind of fun. So the equation sheet that I'm gonna go ahead and email you, that's really easy, and then also I will give you a hard copy on Monday. But on the equation sheet, you're gonna see this equation. All it says, this is Henry's law. I'm like, he got a law named after him for this? Okay. Sometimes instead of C, I'll go ahead and warn you, you'll see like a S, meaning solubility of the gas. C stands for concentration, or S stands for solubility of the gas. All it says is it's related to the pressure of the gas. Now that would be the gas in the headspace above the liquid. Years ago, I was working with analytical equipment where mass spec headspace analysis, or I don't know, but anyway, that's why I use headspace. Now the KH is a constant. Like we have freezing point depression constants, the KH is a constant. But the KH is so picky. Oh my gosh. So the KH is Henry's law constant. The C or S of gas, solubility of gas, C of gas, concentration of gas, that's how much gas is going to go into your liquid. KH is Henry's law constant, and like I said, I have next slide coming up to tell you how picky it is. It's picky for temperature, it's picky for the solvent, the liquid solvent, and it's picky for the gas. Okay, and P, again, pressure of the gas, that's what is in your headspace. Okay, cool. So, concentration of gas, it doesn't have to be moles per liter, but it's a good concentration. Moles of, in this case, this would be moles of gas per liter of liquid solvent that you're pushing the gas into. Units of the pressure of gas could be millimeters of mercury or atmospheres. And if that's the case, then we have set in motion what the units of our Henry's law constant must be. So for instance, if the concentration of our gas is moles per liter, the pressure of our gas is millimeters of mercury, then Henry's law constant is moles per liter per millimeters of mercury. Let's see if I got this right. Then I hate when they have extra slashes like that. But I think what it is, let's see if this works for you. This is like a major divisor right here. So what it really means is moles per liter, and up here is milliliters. Oh, sorry. Moles per liter down here is milliliters. Final answer. Okay, so that's what we're talking about there. The other one is moles per liter in atmospheres. Okay, so KH, Henry's law constant, depends upon the solutes, that's the gas solutes, the liquid solvents, the identity, and the temperature at which you're making this happen. This might be a good slide to tell you that when we're working this sort of problem, we're kind of looking at the solubility of a gas in water. A lot of times, this can be, you can calculate this oftentimes in a problem if you're given the right information. So if you go to work a problem that's like dissolving gas in a liquid, you're like, I don't have Henry's law constant. A lot of times they gave you enough information to knock one out yourself. Not always, but all right. So when I was getting ready for lecture, I'm like, well, these don't look picky. Well, they really are picky because the solvent is water. Okay, the gas is given nitrogen, oxygen, carbon dioxide, and the temperature is 25 degrees Celsius. So again, yeah, they're pretty picky. Okay, so these are moles per liter. Big M means molar, moles per liter per millimeter of mercury. And I feel like we might have even seen this when we looked, when we talked about intermolecular forces. Water is polar, right? And then we see how can we get these gases to dissolve? Well, I'm thinking nitrogen, polar, nonpolar. Nonpolar. How about oxygen? Nonpolar too. Do you guys remember carbon dioxide? Nonpolar. At 50 chance. If you draw the Lewis structure, and again, I'm thinking probably for your test, I will give you the Lewis structure of carbon dioxide. You'd see that it's carbon double bond oxygen. It's linear. Yep. And so the center of negativeness and positiveness coincide. So it's nonpolar. So we have three nonpolar things, gases that we're trying to dissolve in something that's polar. So which one is most soluble?
CO2?
Yep, I think so too.
Non-polar and non-polar water.
This is CO2 is non-polar, dissolving in polar water. So why is CO2 higher than these other two? You think? Because we have this would be an example of what induced dipole to get these two things to stick together. So these would be the strongest in molecular forces because it's the greatest solubility. So like when it combines with water, it's sticking best. Why can we induce a dipole on it better than nitrogen or oxygen? Size. I'd go with size. I don't have a molecular weight for these, but yep, the size in CO2 makes it more polarizable, and so its solubility is greater. All right. So let's get to a problem. I think I only have one problem. Two problems? One problem. This is a busy problem, so let's write it on the board, shall we? But sometimes there's more information than you need. Okay, I could draw mountains. Here's my mountains. And this is my lake. Okay, so this is Bear Lake. Gives my elevation. I don't really need to know my elevation. The partial pressure of oxygen is 0.14 atmospheres. So I'm going to draw a down arrow. What that means is my partial pressure of oxygen, so I'll do a P sub O2 is 0.14 atmospheres. What is the maximum amount of oxygen in parts per million that can be dissolved in the lake at 25 degrees Celsius? So I'll just do T is equal to 25 degrees Celsius. I'll put question mark, and then down here in the lake, question mark, parts per million O2. It gives me a Henry's law constant, so K sub H for oxygen dissolving in water at that temperature is 1.66 times 10 to the negative 6th, and units are moles per liter, and also in the denominator we have units of millimeters of mercury. Cool. Well, right off the bat, I told you Henry's law constant is Henry's law equation seems pretty straightforward. Remember that we can knock out the concentration of O2 is equal to Henry's law constant, which we have here, times the partial pressure of O2. So don't make it harder than it is. The only thing I see is we're going to get concentration in terms of molarity, and we're going to have to remember how that works to get it in parts per million. That's probably the hardest part of this one. All right, so yep, that's the equation we're going to use. And there you see it plugged in. So oh, sorry. So why did I have to do this step, do you think?
So you can put in
Right. I had to make these two units of pressure agree. So I took my partial pressure of oxygen, 0.14 atmospheres, take it times 760 millimeters mercury over 1 atmosphere, round it to 2 sig figs. That means I'm dealing with a pressure of 1.1 times 10 to the second, which is the same thing as 110 millimeters of mercury. All right, now I'm going to plug in. Goodness gracious. So my first term is my KH, which is 1.66 times 10 to the negative 6th. And units of this KH are moles of O2 per liter of solution, also in the denominator, millimeters of mercury. And then my last term is that pressure in millimeters of mercury I came up with, 110 millimeters of mercury over 1, or 1.1 times 10 to the second millimeters of mercury over 1. Notice my units of millimeters of mercury cancel, which they should, and I'm left with moles of O2 per liter of solution. To 2 sig figs, it looks like this. 1.8 times 10 to the negative 4th moles of O2 per liter of solution. All right. So now we need to remember what parts per million mean. Well, in dilute aqueous solutions, parts per million are approximately equal to milligrams per liter. Or maybe, I don't know, I can't remember what it is. Yeah. So if that's the case, can you see where all we got to do is get it from moles per liter to milligrams per liter? So how do we go from moles to grams? Molar mass. Exactly. So what's the molar mass for O2? 32.00 grams per mole. Yep. So we use 32.00 grams per 1 mole, so units of moles cancel. And we're after milligrams per liter. So what's one more term we can put in order to get from grams to milligrams? Yep, 1,000 milligrams over 1 gram, exactly. Yep. part of the deal is you had to remember that milligrams per liter for aqueous solutions is the same thing as parts, milligrams per liter, yeah, same thing as parts per million. All right, rounded to 2 sig figs, because that's what I have in the first term. I get 5.7 milligrams of O2 per liter of solution, which is approximately 5.7 parts per million. Now it looks like we're not going to finish today because we have one more problem. So you would have enough to do this. But now you guys have questions at the end of the chapter. So yeah, instead of worrying about knocking out homework for chapter 12, I would do those.
So even for 13 minutes.
Yeah. So yeah, for 13 will be due. Okay.
Okay.
But this won't be due until Wednesday.
I forgot about this question for a minute. I was like, how am I going to study it? No.
Yeah.
That's good.
Yeah, that'll help hopefully.
How big is this test going to be?
It's weighted